Okay, 25 minutes,
okay.
maybe. So, hello, I'm Tristan Jengol from the GHDL project. I'm the main author of this project. And, well, this is my first presentation about GHDL, so I will speak about on several topics, about of the history, of the present features. I will have a short internal overview of the software, and I have also a few slides on the ideas, several ideas that could be discussed later or never. So for the reference, well, we have changed the project move from GNA.org to SourceForge recently, well, last year. So you can get an up-to-date copy of GHDL from this site. The sources are available, of course, and there are binaries for Linux, Mac, and Windows. You can, if you have an issue, you can create a ticket on this website, and I'll read the tickets. The mailing list is still on the old site, but you can subscribe. If you want to post, you have to be subscribed, so there is absolutely no spam. And if you don't want to subscribe, I have to manually allow your mail. It can take time. So the history of the project is well, quite simple. I started to, my first contact with the language was in the 1997, and at this time, well, I was using tools from FPGA vendors, and at this time there was absolutely no free simulator. So in order to learn a little bit more the language, and because I wanted to use it at home, I started to write the project. And well, 5 years later, I make a public release. So the first public release was well, 12 years ago, and it was already well, quite complete VHDL simulator. The first step of the tool was never public. So it's a free and open source VHDL simulator. It doesn't do synthesis, so you can't create a netlist. It's a pure command line tool. There is no nice graphical interface. Sorry. You can dump waveforms from the simulation in several formats. And there are nice tools, GTK Wave, that is well known, that can be used to display and navigate among the traces. Well, it's well, command line is nice. Yeah, for. Yeah. So, part of the internal view, in fact, it can be considered as a GCC front end. So there's a parser and analyzer. It's linked directly with GCC and use GCC to generate code, well, to generate the object code. So it's fundamentally it's like the C or the GCC C compiler or the G Fortran. You see only one tool. There is no intermediate C code generation. And you can optimize well, you can optimize with -O, or you can generate debug information with -G. You can use gconf to convert your VHDL code. Well, you have all the functionality of GCC. Recently, last year, I also added LLVM backend. So it's like GCC, but using the LLVM code generator. And there is also a built-in code generator that I call mcode, which can generate code either in memory or on the disk. The quality is poor. there is well, no optimization. It's slightly better than GCC-00, which is, as you may know, very, very bad code, but is much slower than GC-0. And the main advantage is that it compiles very quickly. It's very, very fast, and it doesn't need a lot of memory. And when you have big VHDL model with the M code generator, it's very fast and almost immediately. And the build is very easy. It's well, you just download, configure, make, and up, it works. Which is much easier than loading also, well, downloading also GCC, configuring GCC, mixing the sources. Well, the build is very easy. We have made effort to have easy build of GHDL. It's much easier than previously. In terms of VHDL standard, GHDL fully supports the 87 standard. So it was the first VHDL, first standard of VHDL. We fully support the 93 standard, which was the first revision, and the, well, I can think it's the common, the most usually revision. We also fully support the 2002 standard, which just added protected types, well, Miller modification and protected type. Not well used because, well, this is just addition for, well, protected types can be used for synthesis, so it's not very widely used. And we have also partial support for the last revision, 2008. Still partial, not complete. Well, at least enough to support the new IEEE packages that do floating, that provide generic package for floating point and fixed point types. There is also support for SDF annotation. So there is a parser for SDL file and to back annotate the model and to add the timing information. It's not very, well, can be useful, but not widely useful. There is well, partial support for PSL. I don't know if you know PSL. It's property specification language, so you can add assertion in linear logic, and so that are handled by GHDL, and you can also add coverage information. So you have, for example, you can check that if a signal is true, then another is true at least 3 cycles later, but not after 10 cycles. There is a partial support of VHPI and VPI. So VPI is for the, well, it's a very log view of what is VHPI. It's standard interfaces to access information from the simulation at runtime. So you can read the value of signals from a C function. There are also some few, well, nice tools. There is a HTML pretty printer, so it colorizes your files and also add cross references. So if you click on an identifier, you see where the definition is. Well, it's not very complex to do, but it's the kind of things you can do easily with GHDL. In terms of distribution, we try to do release every year. We try for, well, the common OS. We know it works on Linux, Mac, and Windows. I think on Debian it was also at least a few years ago widely distributed on many platforms. So it was also working for PowerPC. Well, using GCC code generator, you can port it on many platforms. Sources, there is, well, last time I checked, at least for writing the slides, it was 150,000 source line of code. The sources are almost written in Ada, with a very tiny part in C and assembly. So the use of Ada is, could be very strange for an IDEA project. There are two reasons for that. First, that VHDL was written using the Ada language. So most of the syntax and the semantic of VHDL directly comes from Ada. So if you understand well Ada, you will understand well VHDL. Or conversely, if you don't understand Ada, you will have trouble to understand VHDL. The second reason is, at that time, I wanted to learn VHDL. Well, it was also a reason to write the GHDL compiler. And I also wanted to learn Ada. So to learn, to create a project. And if you want to learn two languages, create a compiler in another language. Use of Ada is very strange, but Ada is very well suited for large programs. It uses strong typing, very strong typing. C and C++ are not, are less strongly typed than Ada. It's a very well structured language. There is a good compiler, the GNU Ada compiler, with very good portability. Well, GHDL is not a small program. It's maybe not huge, but still a large program. And the use of Ada was very well. I don't regret that because it allows you to structure, it forces you to structure your program correctly. And for refactoring, it's very easy to refactor in Ada because a lot of issues are caught at compile time. Yes?
Did you take inspiration from the Ada frontend of GCC to write GHDL?
Yes.
So
yes.
There is an Ada frontend written in Ada.
Yeah. Yeah, there are a few good ideas in the GNU Ada compiler that are worth considering. GHDL is like, well, I would say any other compiler. So there is a scanner, a lexical analysis, syntax analysis, semantic analysis. There is a a path to expand the code, and then finally it is translated into object code. So the scanner for lexical analysis, it's common compiler notion. So it tokenizes the source file. This path handles number, strings, bit strings. It detects reserved identifiers. It handles comment. There is a special handling of PSL tokens because PSL is not regular VHDL. And like everything, it was manually written. No use of tools such as legs. Well, it's a very common path. The syntax analyzer, so the purpose of this path is to build a tree from token. So it's a parser. There is one source file that defines the tree. Good news is that the VHDL grammar is well expressed, particularly if you compare with Verilog grammar. Well, that's come from Ada, of course. There is a recovery on error, but could always be better. But it's difficult when you write a parser to know what are the common user errors. It's not written anywhere. So when I get report, I sometimes improve the parser. Could always be improved. And it's of course manually written. It's a recursive dissonant parser, nothing nothing very complex. Semantic analysis. The purpose of this pass is to resolve names. So when there is a name, you have to connect it to the declaration of that name. The purpose of this pass is also to type expression. So you have to compute the type of each expression. It also disambiguate notation. I will speak a little bit about that. And this pass is the largest pass because most of the rules of the language are expressed in terms of semantic. For example, a constant cannot be assigned is not a rule written in the grammar, it's a rule written in the semantic. So you have to understand if you write A colon equal B, you have to know what is A to apply this rule. And you know what is A only when you resolve the name. And there is also handling for scopes and visibility. The strange thing that comes from directly from ADA is that the VHDL grammar is ambiguous. I have a few slides on an example. My favorite example is what means A of B. So if you know VHDL a little bit, you will guess that it might be an array index. So here A is declared as a bit vector, and B just select an element of the vector. So A of B can be array index. If you know VHDL, you could say, it could also be a slice. The difference is that A is still a bit vector, but B, in this case, is a subtype. And the subtypes has a range. So this notation is called a slice and select a sub-array of A.
So you mean you need to know the semantics to solve the syntax?
Yes. Well, the grammar is ambiguous. But the same is true for C or C++. And that's what makes semantic analysis difficult, not easy, not straightforward. And if you know VHDL, you would say, this could also be a type conversion. So here B is is an expression for a constant, and A is a type. So this notation means convert B to type R, which is integer. And it can also be a function call. So here A is the name of a function A, and B is the expression here is constant. It could also be a procedure call. So the difference between a procedure and a function is that the function returns a value, and the procedure is a statement. Procedure call is a statement. So here the context help, but it's the same notation. It could also be an index of a dereference. Here A is an access to a string, and there is an implicit dereference of the access, and then followed by an index. So the meaning of this notation is first dereference A, so access is like a pointer, first dereference A, and then select an element of this name. It could also be a slice of a dereference of a name, so like a slice, but with an implicit access dereference. It could also be an index of the result of a function call. So here A is a function that returns a string, and string is an array, so you can select an element, so you can write that, it works. It can also be an implicit, a slice of an implicit dereference of a call. So like previously, A is a function that returns a string, an access to a string, there is an implicit dereference of the string, of the access, sorry, and you select a slice of the string, so a sub-array of the string. So that's what makes the semantic analysis a little bit complex. Particularly, if you don't forget, there is also overloading in VHDL. So the same name can designate several functions. You have to select the right function, and the rules are very strict. There are also use clauses, so you can import, well, have visibility to identifier declared in a different package outside of the current scope. There are also default expression. So when there is a function call, some argument can be omitted. And there are also ambiguities on selected names. Sometimes selected names select an element from a record. Sometimes it's an expanded name, so it selects a declaration from the scope. So that's what makes well, semantic analysis a little bit complex. And I think the result in GHDL is quite good. Sometimes, well, I try to follow very closely the standard. And unfortunately, it's not always a good idea, because sometimes I got report, this design can be simulated by this commercial simulator, but not by GHDL. Okay, so I look at the source, and I say, sorry, but this is not legal in VHDL. I can point to the FOSDEM manual, and so the user is embarrassed, and it's particularly not nice when this is standard package, well, package provided by vendors that have that are not correct VHDL. So I have also added flag that make GHDL more tolerant. But if you want a strict analyzer, GHDL is very good. Hmm? Yeah. Sorry? Well, there is no standard test suite for VHDL. Well, there were a few test suites, but often it's not enough. But it's difficult to cover the standard with a full test suite. Well, it's difficult to write a test suite to cover the full standard. There's always case you forget. So after semantic analysis, there is a phase that I call canon that mostly, in fact, transform concurrent statements into processes, so it extracts sensitivity list in order to make the code generation more easier. There's also work done on the configuration. So that's a technical detail. And after that, there is a phase that does the code generation that I call translate. It's also a complex path. Basically, it takes the tree and translate the VHDL tree into GCC tree. In fact, we are using an abstract API that I called Ortho, which is very simple, strongly typed, very structured. And from this API, I can connect to either GCC, LLVM, so the internal code generator, or I can also dump this tree. And well, all of that is very useful, particularly debugging if you want to, well, to debug the translation path. It's very well. It's much easier when you see what is generated. And finally, the last part of the GHDL sources is what is called GRT, which is the runtime. So what is come with your design, which is what is linked with the design. Well, it's mostly the event-driven simulator. Well, nothing very special. Roadmap. Well, there are few missing features from VHDL 2008 that have to be added. Well, a few. Some missing features. And also, we always want to improve the speed of the simulation. So that's the near roadmap. For a bunch of ideas for the roadmap, it might be a good idea or not to implement synthesis. It might be a good idea or not to generate an XML output so that once the analysis is done, you can create a custom tool for a VHDL program. No, nothing. It might be a good idea or not to support AES VHDL to be discussed. Well, we have talked about that just at the previous, just previously. That's, well, my few ideas about the EDI community. Well, we have a huge concurrency from a FPGA vendor because they sell or give for free simulator. So it's difficult to compete with such tool. Also, I think it's not easy to find people that know well about how compiler works and that are also interested in electronic science. Well, that's my experience or my idea. Ideally, it will be, well, it's interesting to compare, particularly with compiler community, which is quite large. Just, well, maybe to discuss, is it a good idea or not to have a complete IDE? Also, maybe again to discuss, well, it might be interesting to compare VHDL with Verilog. Well, not at the detail, but at the general process. Apparently, the future of Verilog is clear. The future of VHDL is maybe less clear, but it's still widely used. And well, what I think is quite clear that it's very difficult to have new language. There are several tries. I don't know if you know BlueSpec Verilog. Maybe you know, maybe you never used it. I don't know if you know STRL-V7. It was a French startup to create a new, well, formal language for hardware. Disappeared. So the future of IDE language is at least for Verilog and VHDL, and not sure about new language. Thank you.
There's time for a couple of quick questions.
Okay.
Just a quick one. Are you following synthesis or simulation semantics when you simulate? Are you a true four-state simulator?
Well, VHDL is no, yeah, there is no, well, there are two types for simulation. Well, two widely used type is bit type, yeah, or STD logic, which is a nine state. And yes, it's true, it's fully compliant.
Yeah, but
so,
I mean, but I'm a Verilog guy rather than VHDL, yeah, so my apologies if my various bit hazy, but you haven't got 9 types on a physical chip.
Yeah.
So they all have a synthesis behavior as well, which is, yeah, how do I behave if I have to? And so Verilator, for example, Verilog behaves synthesis semantics. Icarus Verilog behaves simulation semantics. Now, it does make a big difference to how you use the tool. So
yeah, sure. Yeah, it might be a good idea to have something like VHDL Lator, yeah, if it is your question.
Let's have one more question.
So, what's your roadmap between the back-to-back and which backend would you consider the most improved?
good question. So the question is about which backend is the most suitable. Well, GCC is widely portable, but it doesn't scale very well with big designs. It becomes too slow. I haven't tried big design with LLVM. That would be a good idea. The nice things about LLVM that it can do also JIT, which is an interesting feature. The internal code generator, mcode, I don't want to spend too much time on it. But it scales very well.
Okay, thank you.
Thank you.